Okay, good morning everyone and welcome to the penultimate day of the conference. So it's a pleasure to have Eloise Hamilton from the University of Cambridge who's going to be telling us about complete collineations for maximum likelihood estimation.
Yeah, thanks Vicky. Thanks to the organizers for organizing the workshop, for the invitation. I'm sorry that I couldn't be here for the previous days, but looking forward to the upcoming talks. So this is a project that's joint with Greg Buxey, Anna Siegel, who's here, Philip Reichenbachs. And I guess the title kind of gives the sort of overarching story of the project. So the idea is to use a notion from algebraic geometry, which is complete collineations, to kind of address from a new angle a problem in statistics, which is related to maximum likelihood estimation. And I guess if you were at Carlos's talk, he will have explained a little bit about maximum likelihood estimation. But in any case, I'm going to assume that you don't know either. And ultimately, it kind of just reduces to linear algebra, so it's not very complicated. So in fact, I can even give the whole sort of the main result that we show with this project, and then the rest of the talk will be about making that more precise. So the kind of starting point is that we have some initial data, like maybe a series of measurements that we've made, and what we're trying to do is kind of find the right statistical model that sort of predicts that data. So you start off by kind of guessing the kind of probability distribution that you'd like. And you have your data, and you now have your model with kind of undetermined parameters, and what you want to do is find the parameters that basically maximize the probability that this model will predict that initial data. And that's precisely the maximum likelihood estimate. So these two things give rise to the maximum likelihood estimate, which I'll just call MLE from now on, given the initial data. And if you remember from Carlos's talk, basically, there are sort of different ways that this maximum likelihood estimate can behave. So the best case is that the MLE, given your initial data, exists and is unique. So that means that you have a unique kind of canonical set of parameters, and that's what you should use for your model to predict that data. And in this case, I'll just say that's the situation where the MLE is identifiable. If it doesn't exist and is unique, then sort of different things can happen. Either it could exist, but there could be infinitely many, and that's problematic because you sort of now have loads of different possible parameters that you could pick, and you don't know which ones you should take. Or it could even just not exist, and in Carlos's talk, there was, he introduced, the likelihood function, and there are sort of two ways in which it could not exist. Either the log likelihood function is unbounded, or is bounded, but the limit doesn't exist. And I want to kind of package all those situations that aren't exist and is unique into sort of one bucket, and I'll just say in that case, the MLE is not identifiable. And somehow this is the case that's extremely desirable, and this is the case that's kind of, what do we do? Because ultimately what we want is that kind of unique set of parameters for the model. So the project is really just about what to do in the situation where the MLE is not identifiable. And the idea is really simple. So you start with the initial data y. Let's just call it y. And I'll sort of be more precise about what y is later on and so on, but I just want to tell you the idea. So this is where complete collineations come in. So basically, we start off with some data that is kind of badly behaved in the sense that the MLE given that data is not identifiable. And then what you do is we're going to choose a complete collineation. So I'll explain what that is when the time comes. But the rough idea is that we use a complete collineation to kind of perturb that data. So we're going to construct a new sample, y tilde, which will be y plus some perturbation y prime that will be kind of determined by this choice of complete collineation. And this thing will be much better behaved in the sense that its MLE will be, the MLE given this new sample will be unique. And of course, we can relate this back to the initial one by just taking y tilde of epsilon to be y plus epsilon y prime, and then taking the limit as epsilon goes to 0, and we recover y that way. And so the whole kind of the results that we prove in this project are about relating the MLE given this and given this to one MLE given the initial sample. So the results are along these lines. So first of all, we show that the MLE given y tilde exists and is unique. And that's kind of only a first step because it sort of seems a little bit, I mean, it's like saying we're interested in this is our initial data that we're really working with. So sort of saying, well, let's just consider a different sample and use that MLE. Somehow it's not really we need to relate that back to the original problem for it to be helpful. And so the remaining results are about relating that back. And that's where the properties of the complete collineations come in, because we can actually characterize when the MLE given this kind of perturbed sample is actually one of the MLEs given the original one. So I guess I'll say like can characterize when MLE given y tilde is an MLE given y. And so there are two cases. You make this perturbation, and either the MLE given this guy is already an MLE given y, and then you're kind of done, because it's kind of saying that's the set of parameters that you get from this one, which is a correct set of parameters given this, that's what you should be working with. But it could be that the MLE given this is not an MLE given y. And then the third kind of result is that by taking this limiting thing, as the epsilon tends to 0, the MLE given y tilde of epsilon, which was, I mean, it's also unique for any epsilon non-zero, that will tend to an MLE given y. So the kind of the result, the main result really is actually just proving that that limit of the MLE given y tilde of epsilon actually exists as epsilon tends to 0. So MLE given y tilde of epsilon exists and is an MLE given y. And of course, this only makes sense if the MLE, like if there exists at least one MLE given y, but if one doesn't exist, then you can sort of restrict to the kind of, I'll explain this later, but you can restrict to the components of the MLE that actually do always exist, and then the result remains true for that part of the maximum likelihood estimate. So the kind of idea is just if you have a sort of bad sample, use the idea of a complete collineation to kind of move it slightly, look at the MLE that you get there, and then take the limit, and that kind of chooses for you like a correct set of parameters, or a sort of, I don't know, canonical set of parameters, which will depend in some cases. I mean, a priori, it will depend on the choice of complete collineation. And what kind of surprised us is that for certain classes of, well, so for linear regression models in particular cases, what's interesting is that it doesn't matter which complete collineation you use to perturb the sample. When you do this process of taking the limit, you always get to like one specific maximum likelihood estimate given the initial sample, which was like not at all, I don't know, we didn't really expect that, but it's kind of neat in the sense that it tells you that your initial sample, there were loads of possible MLEs, and it's kind of saying that there's one in particular that's kind of statistically meaningful because it's the one that you get by sort of perturbing your sample using a complete collineation and then taking the limit. But this doesn't always happen. This is a sort of special to the linear regression models case. Okay. So y tilde is this guy, but yeah, you can just take it a y tilde of 1. Yeah. But it's also true for any non-zero epsilon. Okay, so let me just make, I mean, the goal of the talk is really just to make all of this precise, or a little bit more precise. So So I'll start by talking about just maximum likelihood estimate. So all of this is valid for not sort of any multivariate Gaussian model, but the specific class of so-called DAG models, Directed Acyclic Graphical models. So I'll explain what those are and then say something about MLEs for such models. Okay, so in general, like the kind of the class of models that we're sort of working underneath is these multivariate M-dimensional Gaussian models, which I think were introduced in Carlos's talk. And what this is just a set of probability distributions, and each distribution is determined by its sort of covariance matrix and its mean. For simplicity, we just assume that the mean is 0. So all that matters is the covariance matrix. So you can kind of parameterize such a model by the set of covariance matrices, which is a subset of positive definite m by n matrices, so inside GLM. And so the particular class of models that I'll be talking about that we work with in this project is the class of directed acyclic graphical models. So we start off, so it's basically a model of this kind that's completely determined by a graph. So we have our graph G with our vertices and, like, say, edges between them. And, oops, maybe I don't want this one. Let's just go here. And directed just means that the edges have sort of directions. And acyclic just means that we can't have a cycle in there. So maybe I can do this. Okay, so how do we define a model from this? Well, we need to give the set of covariance matrices, and that is the set of, so identity matrix minus, I'll explain what lambda is in a second, and what omega is in a second. So we take the inverse and then the conjugate transpose. I'll write that like that. And it's the set of matrices of this form that actually lie in the positive definite cone. So these matrices here have restrictions that are determined by G. So lambda is an m by m matrix, and let's say its entries are like this, and it has the property that lambda ij is equal to 0 if there is no arrow from j to I. So I'll say if j is not a parent vertex of I. And omega is a diagonal matrix. So this is, like, let's just write the diagonal entries omega I. And so this, I guess, how to think about this statistically, this kind of model is encoding sort of causal linear relationships between sort of noisy variables corresponding to each of the vertices. So sorry, here I should really put mg, because it's determined by G. So mg, this model, encodes a linear structural equation. So y equals lambda y plus some noise, and that is omega is kind of captured inside this epsilon. This is the lambda. Okay, so that's what I want to say about the models. So now let's turn to samples. So what is a sample? So we just collect independent samples, which is just sort of measuring each vertex a certain number of times. So let's call them y1 up to yn, and each of these is an m vector of length m, so km. So k, so for this whole talk, k can be either r or c. So everything that we say is kind of has a version over r and a version over c. We collect independent samples like this into a matrix, into n by m matrix Y just by putting the columns, the vectors next to each other. Okay, and so now I can talk about the maximum likelihood estimate. So the MLE given Y, so what I'm going to say now is sort of valid for up here in this level of generality, is a particular probability distribution in this model, so some sigma in this M, that maximizes the likelihood of observing Y with this model. So that maximizes the likelihood of observing Y, i.e. That maximizes the likelihood function, which is a function that depends on the sample, and it maps this covariance matrix to the product of F sigma of Y, which is the sort of probability density function of the Yi, sorry. Anyway, this doesn't really matter if you don't actually know the formula for this, because I don't think I can write it down from memory. So that's what the maximum likelihood estimate is. And I guess the main sort of observation to make is that it could exist, and it could, well, so first of all, it may not exist, as I said at the beginning, and if it exists, it may not be unique. May not be unique. But for these kinds of models that we're interested in, we can be a little bit more precise about like what it means to exist or not exist, and kind of which parts of this MLE may or may not exist and may or may not be unique. So I'm going to make sort of two further definitions. So in the case of these DAG models, so I call these we call these DAG models. In the case of DAG models, we can define the lambda MLE given Y is, as the name suggests, it's the lambda part of sigma hat. So is the lambda hat component of sigma hat, and then similarly the omega MLE given Y is the omega hat component of sigma hat. And what I'll do is I'll give you a sort of formula for these from which it will be clear which of the two kind of may or may not exist and which of the two may or may not be unique. So maybe I'll do this on another board. So let's start with the lambda MLE. So for every vertex I, what conditions do the lambda ij hat satisfy? They satisfy the condition that if I take the ith column of my sample, of my matrix, and I project it onto the span of the columns yj, where j is a parent of I. So if I do that, then this is inside the span. And so I can write that as a linear combination of the vectors in the span. And I just want that these lambda ij's are coefficients that make the equality hold. Okay. And so we can see from this that the lambda MLE always exists, because if I just ask how do I write this projection, I can always find coefficients such that this is true, but it may not be unique, because if the vectors in this, the parent columns are not linearly independent, then there could be many ways of writing this as a linear combination of the parent columns. So the lambda MLE always exists because you can always find coefficients, but it may not be unique. Yeah.
So you have n samples.
Yes.
And this is lambda is an m by m matrix.
Uh-huh.
So I see y sub I indexing over m, but I see y sub I indexing over n here.
Oh, right. You're right.
Yeah. But I think we understand.
Wait, sorry. What's?
Okay. So.
Oh yeah. Sorry. Yeah. I've made a mistake. It's because actually. Yeah, so sorry, in the middle of the project, we switched around the matrix, and so I've written this wrong. So
I guess you mean the rows or something?
Yeah, well, so here it's an, let's assume n is really big, so it's like this. So yeah, right, so my samples here are rows, so actually I should change my notation, thanks. So this, yeah, let's put j here. I, j. I think that's okay now. Yeah, thanks a lot for that. That's
but that's like the whole list of all your samples.
Yeah, exactly. So this is yeah. I put my samples in the rows, and those are the columns. Yeah.
But okay, so each of those is a large vector.
Exactly. Yeah, it's a lot. Yeah. Yeah. Sorry. So thanks. So these are the columns of my matrix. Okay. So the lambda MLE, it always exists, but it may not be unique. And then now let's talk about the omega MLE. So for all I, what is omega I hat? Well, it is the, let me write this down. Okay, so it's just, you take the norm squared of the distance between this vector minus yi. So yi minus its projection onto the parent columns. Y I, and actually you take 1 over n, I think. Yeah, and this is only if it's non-zero, because this matrix omega has to have non-zero diagonal entries to lie in so that this thing lies in the positive definite cone. So what this is telling us is that the omega MLE, it may not exist, but if it does, then it's unique. Then it's unique, because it has this kind of closed form expression. And in some ways, what we're mostly interested in is the lambda MLE part, because it always exists, and the problem that we're trying to resolve is like the case where you have many possibilities for parameters of your model, and you want to sort of find in some sort of canonical way, like a sort of a single set of parameters. So in the rest of the talk, I'll keep saying MLE and talk about like the MLE given y, but in the case where it doesn't exist, then just replace that with lambda MLE, and then the statement will remain true. Okay. So now I'll give a theorem from a paper by Visu, Makam, Anna Siegel, and Philip Reichenbach from 21, I believe, where they basically give these formula and characterize sort of give criteria for a sample that ensures that the MLE either exists or doesn't exist, and so on. So I'll write that down. So the MLE given y. And so this paper, I should say, builds on the paper that was presented in Carlos's talk. So the MLE given y exists. Actually, let's say that I'll start with does not exist. Maybe I need a bit more space to write that. does not exist if and only if there is some vertex I such that the ith column of my matrix lies in the span of the parent columns. And so taking the negation of that, it will exist if and only if for all I, yi is not in the span. Oops, sorry, I might make this mistake a few times, like putting the index at the bottom when it should be at the top. So if and only if this is true, and then it exists and is unique if and only if for every vertex I, if you look at the matrix formed by keeping only the column indexed by I and the column indexed by the parents of I, so let's write this as parents of I union I, then that has to have full rank. And it's sort of not surprising that these conditions come out when you think about how these these formulas, like it's kind of having this unique lambda MLE is kind of about these things being linearly dependent and so on, and independent and so on. But I needed to present this because this leads on to where complete collineations come in. So be all right here. So. So from samples to complete collineations and back. Basically from y to y tilde and back. So one thing I should say is that if we look at this, then how could it be that the MLE given a sample doesn't exist? It can kind of happen roughly in two ways. One of the ways is that you don't have enough data, like your n is too small, and then there's just no way that you can have this condition be satisfied. So that's one way. Or you might have loads of data, but it's sort of not generic enough, and so you get sort of lots of dependencies amongst the columns, and then you sort of fail to have a unique MLE. So there are these two cases, but really, if you're in the situation where you didn't have enough data, like your n was too small, it was like smaller than m, then you could just kind of duplicate that data, like copy-paste it enough times so that the number of samples becomes bigger than m, and then you're in the situation where the columns of the matrix are sort of not, the data is not generic. So basically all this to say that somehow from here on, like without loss of generality, I'm always going to assume that n is bigger than or equal to m. And that's just going to be relevant right now. So we have our sample y, which is an n by m matrix, and sort of by picking the standard bases for these, for kn and km, I can think about this as a linear map from km to kn. And if the MLE given y doesn't exist, then, so if MLE doesn't exist or is not unique, then that tells us that F is a degenerate map. By non-degenerate, I just mean like full rank. So here's where sort of kind of the philosophy of algebraic geometry comes in. It's that the reason why this sample is sort of badly behaved from a statistical perspective is because as a linear map, it's degenerate. And one of the kind of important ideas in algebraic geometry is to study non-degenerate objects by studying degenerations of them. And something that comes up that occurs quite often is that when you're studying degenerations, what you care about is not just where you arrive. It's not just the degenerate map that you arrive at, but it's also how you degenerated. And by keeping that information, both of the degenerate thing that you arrive at and how you degenerated, that's how you kind of can use, that's how you can sort of get information about your initial object. And so somehow what's happening, the kind of philosophy of what's happening here is that our perspective is that there's not enough information here. Like the information we should have is not just a degenerate map, but we should have information of how this map has been degenerated from a non-degenerate map. And complete collineations are in a way like the perfect thing. Like it sort of tells us exactly the kind of information that we should encode in a degeneration of a non-degenerate map. So let me define some things. So first of all, a collineation. So here, instead of thinking of maps from vector spaces, we'll think about maps from projectivized vector spaces. It's not, it doesn't really matter, but it's just because sort of projective things are nicer in algebraic geometry. But a collineation from, so I've got a vector space V and a vector space W. And I'm going to here assume that the dimension of V is less than or equal to the dimension of W. And so this is where, I mean, later on we'll take V to be Km and W to be Kn, and that's where this kind of, without loss of generality, n bigger than or equal to m becomes relevant. And so a collineation is just the scalar equivalence class of a linear map, equivalence class F of a linear map F from V to W. And sort of collineation because it will map lines to lines, basically, if it's non-degenerate. So, and okay, so before somehow I'll define complete collineations in a kind of roundabout way. I'll first define a space that will be called the moduli space of complete collineations, and then a complete collineation, by definition, will just be an element of that space. And then I'll give a definition that's like a bit easier to work with. So, so the moduli space of complete collineations from P of V to P of W is the closure of the graph of a rational map phi from, so I take my space of collineations, which I can parameterize as the projectivized HOMs from V to W, and I have a rational map to projectivized HOM from the second exterior power of V to the second exterior power of W, and so on. I keep raising the exterior power until I hit, let's call dim VR until I hit lambda R. And what is this map? It's just taking F to the second exterior power of F, the third, and so on. And this is not defined on all of this because if it's degenerate, then some of these may be 0, and therefore they don't give me well-defined points in these projector spaces. But the important thing to note is that this map is well-defined precisely on the locus of non-degenerate collineations. And so the moduli space of complete collineations you should think about as being a sort of alternative compactification to the space of non-degenerate collineations. Of course, this space here is perfectly reasonable compactification. It's very simple, but geometrically, it's not very nice. Like its boundaries are very complicated, whereas the boundary of the moduli space of complete collineations is very, very nice. So from the point of view of algebraic geometry, in terms of answering, doing some enumerative geometry, it's just much nicer to work with this, this moduli space. So let's call this space M. So a complete collineation from P of V to W, P of W is an element of M. Okay, so the thing is, like, if we define a complete collineation in this way, so what this M is living inside the product of this and this, and if you start off with a point in this bigger product space where the first term is degenerate, then it's actually really not obvious to figure out what must the subsequent terms, like what condition must they satisfy to actually lie inside M? Like what does it mean for it to be coming from a degeneration of a non-degenerate map? But just coming back for a second to what I said earlier about like complete collineation kind of gives you exactly the right information that you need when you degenerate. It's like, it's basically saying if you just think about a degenerate map as being the only data you get from degenerating, it's just remembering sort of the map itself. But when we do this kind of, this construction, you should think of these as like the kind of I-plane to I-plane correspondences coming from F. And what kind of philosophically, what the moduli space of complete collineations is doing is it's encoding how these I-plane to I-plane correspondences degenerate beyond just how does F itself degenerate. So that's kind of what I meant by if we have a sample with a non-identifiable MLE, we should really be thinking about it with some extra information that the complete collineation gives to us. So coming back to this problem of it's not really easy to figure out exactly what a complete collineation should be as an element of this product space, there's another perspective that gives us a nicer kind of description of what a complete collineation is, and that comes from describing this moduli space in a different way as a sort of sequence of blow-up. So you start with this, so this is due to Weisinger in, I think it was 1985, and he explained how you can reach M by taking this projectivized Hom space, you look at the locus of rank 1 collineations, you blow that up, then you blow up the proper transform of the rank 2 and so on, and then he just shows that the thing that you get is actually the same thing as this moduli space. And when you look at it from that perspective, it's actually easier to sort of describe what points in that moduli space look like from the blow-up perspective. And so let me write down equivalently. Yeah.
Is just coincidence that it's the same M as the model, right?
Where is
the M from the moduli space?
Oh yeah, sorry. It's just because I wrote it small, but I really, it's like, I mean like a big capital curly M. Oh, sorry. Oh, sorry. I see what you mean. I see. It is completely coincidence and it's bad notation by me. So let's just do like a kind of more curly M. Yeah. So. Okay, so equivalently, a complete collineation is a sequence of scalar equivalence classes of non-zero maps F1, F2, up to Ft, and so F is our initial map from B to W, and then, sorry, F1, and then F2 is now a map from the kernel of F1 to the co-kernel of F1, and then F3 is a map from the kernel of F2 to the co-kernel of F2, and so on, until Ft, which is a map from the kernel of Ft minus 1 to the kernel of Ft minus 1, to the co-kernel, sorry, and Ft is the first non-degenerate map. So basically, if F itself was non-degenerate, then you have like a single-term sequence, and that's a perfectly good complete collineation from P of E to P of W. And in fact, you just think of it as like the element in the product space that's just like F, comma, all of its wedge powers. Okay, so this is samples to complete collineations. Now let's go back. What am I doing? Okay. Okay, so the idea is just, so we start with our sample. I guess let me just call this, where am I up to? Okay, so let's go back to samples. So let's fix our F from Km to Kn. And now let's take V to be Km, W to be Kn, and let's choose. So I want to choose not just a complete collineation from Km to Kn, but I also want to pick, I mean, here we're working in that sort of affine world, so I also just want to pick like a choice of representative in each scalar equivalence class. So I'm going to call that an affine lift. F1, F2 up to Fd of a complete collineation from P of Km to P of Kn with F1 equals F. And then all we want to do is just kind of package that back into a sample, like into a sample, i.e. into a linear map from Km to Kn. So it's sort of, it's not difficult to do. You just inductively extend each Fi, which is a map from the kernel of the preceding one to the co-kernel of the preceding one, and you sort of use the sort of standard inner products on both sides to just kind of extend that by 0 to maps from Km to Kn to Fi tilde from Km to Kn. And then let's just add them all up. So let's just define F prime to be F2 tilde plus up to Ft tilde. And really just by virtue of how we've done this, we sort of get this kind of straightforward lemma, which is that F prime satisfies kind of two properties. The first one is that the image of F prime is contained in the image of F, and is the orthogonal complement of the image. And this is kind of just by virtue of them being maps from the kernel to the co-kernel, which you identify as the orthogonal complement of the image. And the second condition is that the kernel of F prime, if you take the orthogonal complement, that is precisely the kernel of F. It's again by sort of the similar strategy. The equality just comes from the fact that like you have to stop when you get to a non-degenerate thing. And so this enables us to make this definition. So given a sample F, we'll call an F perturbation F, I guess, is a map F prime from Km to Kn satisfying 1 and 2. And then we also want to kind of combine that with our initial sample. So, and we define an F stabilization is F tilde equals to F plus F prime, where F prime is an F perturbation. So I've just kind of made precise what I was saying about like right at the beginning about, is it there? It's not there anymore, sorry. I must have deleted it. Yeah, I deleted the wrong board anyway. So it was this kind of like y prime, y tilde. That's how we define it. So let's see what's next. Okay, so I'll finish just this section with actually. Okay, so I'm going to write down a proposition, which is kind of basically a tautology from what we've done. It's the first statement is that the MLE, given an F stabilization, is always unique, and this is because like that's just how we've kind of made it work. Like the whole point of a complete collineation is you kind of like, if you do this process, you're precisely going to get a non-degenerate map. And the second statement is that via this construction, a choice of affine lift of a complete collineation from Km to Kn with first term F will uniquely determine for us an F stabilization just by this construction. So a choice of, I guess, affine lift of complete collineation with first term F uniquely determines an F stabilization. Okay, and I guess, so this is where like this sort of, the last bit of the talk is important, because in a way, I mean, you could have just said, okay, if you have a sample, F, and it's degenerate, then just add any matrix to it to make it non-degenerate. And then you could just say, well, okay, we just define that to be an F stabilization. And then we would sort of get the same proposition. So somehow what's key here is the fact that it's by imposing these two conditions on and sort of to define what it means to be an F perturbation, that we can kind of actually relate the MLE given an F stabilization to an MLE given the original sample. And somehow if we drop these conditions, if we just ask, like if we were just to say an F perturbation is just like a matrix which when you add it to the original one becomes non-degenerate, we wouldn't be able to do that.
So I guess the point is when you have these data, this type of a map like this, you know, there's a way to degenerate each of these pieces to actually get that point in the fiber over F.
Yeah.
By sort of multiplying F prime by epsilon, you start taking like a diagonal degeneration instead of a very like high order one.
Yeah.
Because it's like a T parameters normally.
Yeah, exactly. I think so. Like, yeah, I think that's the idea. So I guess using, so let's say using, how much time do I have? Not so much. Using F stabilizations to resolve non-identifiability of the MLE. Okay, so the key question somehow is okay, great, like we just pick a complete collineation or an affine lift of it. We have a new sample, an F stabilization with a unique MLE, and it's how does that relate to an MLE given the initial sample, if it exists, or if it doesn't exist, how does it relate? How do the lambda MLEs relate? So our first result is kind of a characterization, like an if and only if for when the MLE given F tilde is an MLE given F. So just for notation's sake, let me, so we've got F tilde is an F perturbation. So F, let's say it has columns Fi, and F prime has columns Vi. So the proposition is that the MLE given F tilde is an MLE given F if and only if, whoops, I think it's time for a new, where's the, oh, is it over there? Okay, so this is true if and only if Vi lies in the span of the columns indexed by parents for every I, and the second condition is if I look at the projection onto the span of the parents of, onto the parent columns of Fj, of Fi, and I add Vi, I want that to lie in the span of the parent columns of F tilde. And then just I'll use sort of shorthand notation for this because it comes up often, Fi bar. So if I put the bar over the column of some matrix, I just mean project it onto the parent columns. Okay, so this is something you can kind of just check. So it's nice to have an if and only if like this. And once you have a statement like this, I guess there are like many questions, which is...
So epsilon, is that for all epsilon?
Oh, sorry, that's just absent-mindedness, sorry. There will be epsilon in a second, sure. But not now, thanks. So there are many questions, like once you have this proposition, which is, if, let's say that F, there is at least one MLE, you can ask like which of the MLEs can be achieved as the MLE given a stabilization of that sample. Is it, can each of them be achieved? Can just one of them be achieved? And it's sort of, I guess we didn't really have an intuition for what the answer should be, but what's interesting is that for for linear regression models, so in the sort of context of these DAG models, what is a linear regression model? It's just a DAG model where you have a unique, it's a connected graph with a unique child vertex. So for this particular class of graphs, what we can show is that if there exists at least one MLE given f, then no matter what f stabilization you take, the MLE given that stabilization will always be an MLE given f, and moreover, it will always be the same one. It will be independent of which stabilization you pick. So if there exists an MLE given f, then MLE given any f tilde is the so-called minimal norm. Actually, well, it's not, to be really correct, is the MLE given f with lambda MLE of minimal norm. So what this means is that if that definition is still there, I think, of the lambda MLE, so the lambda MLE is determined by these coefficients. And if in the case where you have sort of many possibilities, this is the lambda ij's are somehow a solution to a linear system of the form like ax equals b, and the minimal norm one is the one that lies in the orthogonal complement to the kernel of A. And so we can show that that's the MLE that you're going to get via this process, independently of f tilde. But this, in the case of linear regression models, this already ceases to be true, even for the lambda MLE, if you don't no longer assume that the MLE given f, or at least one, exists. And I think, and for more general models, there's sort of no reason why a statement like this should be true. But it's kind of interesting that in this particular case, it's like saying the MLE of minimal norm for the lambda component is kind of statistically meaningful.
So is this partially because you're constructing everything with respect to your norm? You're taking orthogonal complements?
Yeah. It's all dependent on some kind of the choice of like standard inner products on Kn and Km. Yeah. Okay, so I'll just finish with one last result, which is so we have this proposition here, and it may be that you take an F stabilization, and the MLE given that stabilization is not an MLE given F because it doesn't satisfy these properties. So in this case, the VIs are the columns of F prime. Sorry, I wrote it really small.
Okay,
yeah. So the last thing I'll write down is maybe I should write at least one theorem. So let's make this a theorem. So the theorem is that suppose there exists MLE given F. And as I said earlier, this assumption, if there doesn't exist one, just replace, then the lambda MLE always exists, so just forget about that and work with the lambda MLE instead. Then pick F stabilization, F tilde. Then the MLE given F tilde of epsilon, which I define to be F plus epsilon F prime. So first of all, this it always exists and is unique for epsilon non-zero. This is related, well, yeah, it's sort of, the argument is no different when you put an epsilon versus just one. Has a limit as epsilon tends to 0, and this limit is an MLE given F. So in a way, this kind of this theorem sort of supersedes this one because you can, I mean, we can basically incorporate it into the proof of this one. So that's kind of like the main result, really. It's just, you know, you start with a sample. You use the sort of we use the idea of a complete collineation to give a definition of a perturbation of a sample, and then we say, okay, so take such a perturbation, and then consider this degeneration back to F, and look at the limit of the MLE, which is unique for each epsilon non-zero, and that will. So the kind of hardest. I mean, all of this is basically just linear algebra, but the hardest part was in a way showing that this limit actually exists. And it's sort of, initially it seemed like, oh, obviously it exists, and it was just a matter of proving it, but actually it's a little bit more subtle than that because, and this is where these conditions actually really come into play. It somehow comes down to like a geometric statement. It's like you have, the problem here when the lambda MLE is not unique is that you have vectors here that are linearly dependent. So when you project yi onto the parent columns, you don't have a unique way of writing this as a linear combination. So what you can do, the whole idea of this result is saying, okay, well, let's just perturb each of these. Like, let's add epsilon vj to each of these in such a way that the span, the new set becomes a linearly independent set. And so, but we're doing this in a way that's sort of constrained by 1 and 2. I think 1 in particular, 1. And so you do this, and you similarly perturb this one because you're perturbing every column of your matrix. So you similarly perturb this. So now if I project my perturbed like yj plus epsilon vj onto the perturbed span, there are some unique coefficients that give me the expression. And I'm interested precisely in those coefficients, which will now be like lambda ij epsilon. So I'm interested in those coefficients. And what we're doing is we're saying, okay, now let's let epsilon tend to 0. And I want to understand the limit of these coefficients. And it seemed like this should always just exist, but actually it doesn't. And it's very important that the perturbation has the property that the vectors of the perturbation are all orthogonal to the vectors of the initial thing, or else you can have counterexamples where like you have, if your perturbation is not in the right way, and you have like, let's say like 1 epsilon and 1 0, and you want to write 1 1 as a combination, you can imagine needing like 1 over epsilon times your vector, and 1 over epsilon certainly doesn't tend to a limit as epsilon tends to 0. So these conditions, the condition 1 precisely ensures that these coefficients are actually bounded, and therefore that the limit exists. So that was kind of like the tricky sort of linear. But the argument really is just linear algebra, or we have a geometric argument for it as well. So that's kind of that's the idea. You just start off with your sample. You take a perturbation. You map it back to sort of send it back to 0. And then the MLE has a limit, and it will be one of the ones of the initial sample. So that's the idea. So, thanks.
Are there any questions?
So am I interpreting it right that when you make a choice of complete collineation, you get a different MLE depending on which one you do? So is there a way of like making a statistically motivated choice of complete collineation that would say that for some reason this limit that you get really is the best MLE?
Yeah, like that's a like really good question. It's something we thought about. So of course, what you want to interpret like complete collineation statistically. So and there's kind of like I just deleted what the definition was, but it is a bit suggestive. I mean, what it is you have your map F, which is your initial sample, then you have a map F2 from the kernel of F to the co-kernel of F, and then the next one, and so on. And so you could kind of think about like picking a complete collineation as a sort of sampling procedure. Like you say, you have your initial sample, and it's not great. So now you take a new sample, but it's not just you're not taking y1 up to yn, where each yi is in km. You now want to take a new sample where when you combine it together, it will give you basically a map from the kernel of F to the co-kernel of F. And then it becomes a bit difficult about how does it like, so it means that if you want it to be a map to the co-kernel, it means that you sort of want to be, you don't want to be sampling each of the vertices, each of the m vertices. You kind of, what you can do is you can identify the co-kernel with the orthogonal complement of the image. You can pick a basis for that. And then what you could do is you could somehow sample the basis. That maybe kind of makes sense. But then the other constraint is that you want it to be a map from the kernel of F, and then that seems a little bit more arbitrary because the domain is somehow telling you how many times you need to sample. So it's sort of telling you you should sample like the number of times is the dimension of the kernel of F, but like then it just, to write it as a matrix, you just make a totally arbitrary choice of the basis for the kernel, and I'm not really sure how to like think of that, or how to, if there was a sort of statistical way of making that kind of canonical. But yeah, the goal kind of ultimately would really be to kind of have a statistical interpretation of the moduli space of complete collineation. Like instead of working with this DAG model, it would be really nice to sort of have a model that's sort of modeled on the moduli space of complete collineation so that a sample is always a complete collineation, rather than like, in a way what we're doing is kind of like a little bit sort of hands-on, trying to put everything back into our initial framework, but maybe we could like change the framework so that like straight up off the bat, you take a sample and it's a complete collineation. I'm just not sure like how to do that. Yeah.
Yeah, so I mean, you have like your graph and then your samples are these coordinates. And when you go to this space, it's coordinate free and
Yeah, exactly. So yeah, I'm not sure. But that's kind of the dream.
So it seems like the number of resolutions that you have to take of your F depends on how degenerate it is. So is there like, or I guess that's kind of like your T. Is there like a universal F that works, or a universal T value that works regardless of how degenerate your F is?
Well, I mean, I suppose if your F was really degenerate, like you could resolve it in just one step if your next map was like sort of straight away. So it kind of, I suppose like you could, you could pick any T and then just like find a sequence that sort of ends in that T. So I don't know. It's kind of like it. Yeah, I'm not really sure how to give a good answer. It's sort of like, I'm not sure there's like, for any T you could just, and you start with any F, you can sort of make, I mean, I suppose you can at most go down by like, the least you can go down by is like one rank at any point. So if your map is not degenerate enough, then if your T is too big, yeah, you'll never reach that somehow.
Like, maybe it's because like after you get to a high enough rank, then your resolutions will just be 0.
Yeah, and you can't have non-zero maps along the way. But one thing to say is that somehow once we kind of package them all together, it's in a way it's like independent of the T. Like that's kind of completely lost once we define perturbations.
yeah, I mean, your result is sort of agnostic because it's all possible perturbations you're showing.
Yeah, satisfying 1 and 2, and it just so happens that 1 and 2 kind of arose through summing them up, but they could have arisen in a different way.
Well, it's all possible perturbations given. I mean, you have F and then there's fiber.
Yeah, there's
Space.
You have every possible fiber. You construct them, so you're very agnostic on which one you take.
Yep.
I think we have another question.
Yeah, so I had a question, a comment. So, well, first, I think, okay, you're thinking about this F coming from the samples, right? And so as Frank was saying, there's like a lot of choices and what's it called? Like there are the ordering of the samples, things like this. But maybe it's better to look at the sample covariance matrix, right? Because so this is really the sufficient statistics in this model that captures everything you need. So I feel like maybe looking at the sample covariance matrix directly could simplify things.
Okay.
Then you also wouldn't worry so much about the sample size because then everything is already encoded in the rank of this matrix.
Right. Yeah. I mean, I remember Anna mentioning sufficient statistics at some point. Like, I guess I haven't seen them so much, but that sounds interesting, and yeah, it'd be good to hear more.
And the other question was, have you considered maybe like omega, not diagonal? Have you tried this extending to other?
No, not at all. I haven't thought about that. I'm not really. I mean, it's like my first foray into statistics, so I kind of just took the definitions and I was like, I'm not going to try to change anything, but yeah.
Thank you.
Are there any other questions here or online? No. I think not. Then let's thank Eloise again.